So the time now is 8:53 Brussels time. My name is Avihu Levy. This is going to be a somewhat technical talk, so I apologize in advance. I mean, maybe it's not the right forum and time, but I didn't actually give this version yet. I gave like a slightly modified version once, and I would like to try and talk about it today. I did cut out everything except of the core, so I think it can go into like, I would say 20 minutes, if I'm not too optimistic here. Okay. I work at Starkware, forgot to say that. So today we're going to talk about basically how, or at least one method that we think can be useful to defining smart contracts on Bitcoin. I'll explain a bit about like why this structure makes sense. But first, like I want to give like a bit on what is needed and maybe like a little bit of background that I assume that people are not necessarily very well aware, but they heard it once in their life. So, Bitcoin state is basically the unspent transaction outputs, as you all probably know. And what that means is that you have transactions. This is a transaction, that's another one, and now we are creating a new one. And transactions are spending unspent outputs. And the way that they are spending those unspent outputs is by satisfying some conditions. Basically, you need to show that you know something in some way that doesn't necessarily reveal this knowledge to others. But once you show the logic, this scroll here, I'm not going to talk Bitcoin terms so much. Once you satisfy this program, and you show this program that you know enough knowledge, then you can spend whatever Bitcoin that are sitting in the output on this program, right? Okay, so basically the state of Bitcoin is just made of those unspent outputs and the amounts there. And just for comparison, what we don't have, okay? So that if I look for, just to compare, if I look on systems like Ethereum, the state is much richer. You have in the state logic of all kind of smart contracts. You have the state that those smart contracts hold. It can be arbitrary. And as a side note that I will not get into today, it's also global, meaning people can call it together without being synchronized. Meanwhile, the Bitcoin state is much skinnier, I would say. And the reason it's skinnier is basically this. So changing the state in Bitcoin, remember the state is the UTXOs, the unspent transaction outputs, and changing the state is based only on knowledge, meaning if you have the knowledge, you can spend the state however you like. You can change the state however you like. There are no restrictions on what you can do with the state. This means that like, just to explain with an example, what do I mean? It's like if you think on systems like Ethereum, you have a state, for example, an AMM pool, for those who knows what it is, and you can access this state, and you can trade against it, but there are rules on how you change it. You can start with a state A and finish with many other states, but you cannot choose to turn this pool into a camel. And here, you can do whatever you want. You can, once you have this knowledge, you can change the state however you wish. And that provides that creates a problem because we have no way or no simple way to work with this to create an actual smart contract that hold what I call persistent logic and state, meaning logic that is immutable, or at least there are rules to how it is defined, that doesn't change with the spender request, but stays immutable until maybe some rules are being applied, and state that is, it's not persistent in the sense that it doesn't change, but it's persistent in the sense that it can only change according to the logic, and it stays there. It doesn't being removed with every new transaction. So this is what we want. When I'm talking about Bitcoin smart contracts, this is what I want to achieve. Okay? Okay, so maybe I'll just say one thing first. It's very, very hard I would say impractical to achieve this in the current setup. Maybe there is like there are things you can do, and maybe some other I would say trade-offs you can take to achieve this. But if you want to achieve it with the same trust assumptions, or with as minimized as possible trust assumptions, and without doing crazy work, then it's not very practical today. So I heard there was a panel, and you guys are already very much aware what OPCAT is, right? I'll anyway just state it in a sentence. OPCAT is an opcode that doesn't exist today in Bitcoin, and it allows one to take two elements from the stack and concatenate them together. And that sounds like trivial for most, I would say most programming languages, but when it comes to Bitcoin scripts, that's not the case. But apparently this tiny feature operation that seems almost trivial can lead to wonderful things. Okay, so yeah, we'll just touch it and we'll move forward. So OPCAT enables holding a state in a way that I will show in this talk. I will show some of it in this talk. It also enables very efficient verification of Starks, and the reason being that Stark is a proof system. How many people are aware what proof systems are, or Starks? Okay, so it's enough for me to assume that most of you know, and if you don't, then come to me after. So basically, Stark is a proof system, meaning it enables people to prove that the computation was done in a certain way and come to a certain output, and then verify the proof in something that takes much less time than running the computation itself. And because it's hash-based, if you provide concatenation, then you can verify it efficiently. It also happened to be the case that the flavor of Stark that we are working on right now is based on very small fields, in particular fields that rely on 4 bytes arithmetic. Those of you who dealt with Bitcoin scripts know that arithmetic can only work on 4 bytes. So by accident, it works very well. And it also enables writing logic in a language called Cairo, which is, I think, well, it's a Rust-like language. It works very well with Starks. I won't get into it anymore right now. Okay, this is interesting. So the arrows represent requirement. The dashed arrow is a weak requirement, meaning you can manage also without it, but it's probably better with it. And so OPCAT gives us state management and Stark verification, and state can give us, in a way that I will show today, smart contracts, and I claim that it's better to also have Starks for them. And then if you have Stark verification and smart contracts, it's possible to create validity L2s, like L2s that relies on proofs and can provide scale, which we won't talk about today. Okay. Do you see the purple arrows? Yeah. Okay, good. So covenants, you probably heard the name, right? Most people heard the name. So the idea of covenant is, if I put it pretty simple, is as following, is the ability for the program, this scroll up there for the witness program, to get the transaction data and be able to know that this transaction data is actually the correct one. And based on the transaction data, do magic that maintains state, that put rules not just on who can spend, but also on how they can spend it. So how this would work? Basically like this. In this example, let's take this for example. So let's say that the witness program, this scroll over there, it wants to check all kind of rules on those 4 boxes that are pointed by the purple arrows, right? So there are like 2 boxes from different transactions, and 2 boxes from the current transaction, but that relate to the output. So how it would go about it, there will be someone, the spender of the transaction, the creator of the transaction, will provide the transaction data, meaning those 4 boxes and maybe some other information. And very hand-wavy, because we will not focus on this. With OpCat, we are capable to take those that transaction data parts that are given to us separately, concatenate them, basically replicate the way the transactions are being messaged in order to be signed. And then once we have that, we will be able to know that this transaction data indeed is the transaction data of the transaction that I, the witness program, am being spent at. So it gives the program the ability to be aware of whatever transaction it exists in, but it's not like it can access it directly. It needs the information from the person who creates the transaction. Do you understand this? Did you get this? If not, it doesn't matter. But if you did, great. The point is that once we have this, we can from now on assume that the caller sent the transaction data, and the witness program, this scroll, can use it inside the witness program. Okay? So here is a much more structured way to do smart contracts. Here is the proposal. It has been proposed by multiple parties, I think Waking Chain and S-Script and probably a bunch of others. And we were also thinking about roughly the same concept. So it looks roughly the following. You have, remember that we said that with covenants, or with OpCat, sorry, we can build covenants, which means we can be aware of the transaction data. Somebody is providing this to us. So in particular, we can say, okay, this witness program can be now receive the information, the data of all the other white boxes in the transaction. So we have here, let's say, a previous state transaction and a new state transaction. And what is happening here, or what needs to happen for this to represent a contract, is the following. Let's for now assume, and then we will make sure that this is indeed the case, that the output, the first output, represent the contract logic. And because of that, what do we want from the contract logic? We want it to remain immutable. So one straightforward way to do that is to say, okay, logic, the first thing that you are going to check is that the same pay-to-taproot address that exists in the first output of that transaction is equal to the address of the pay-to-taproot address in that transaction. And that ensures the logic that it's being replicated, because no other logic can stay there under the same address. Address represents some unique way of representing program, and that means that the program will remain the same program. And then, okay, so we have immutable program, because the program is making sure that you always keep the same address as the first output. And then the next thing that the program will do is it will operate on some state. So for some technical reason, it's much easier if we work with the pay-to-witness script hash. If you don't know what it is, it doesn't matter. Really, put it on the side. It just means that there is a different type of output here, that what we are going to do is we are going to put some data in it, and we call this data the state. And the way we put data is can change with your favorite flavor. One way that I saw people doing it is by using the witness program and put it in the end like op return, and then push data and the state. So, and then they parse it. And they can, remember, for Bitcoiners, they can parse it because they can concatenate strings. For everyone else, I assume that you just assume it because it's, yeah. So in this example, there is, after op return, there is push data of the state S. And what this program logic will do is it will check that whatever the change between the first state S and the second state S prime, whatever change happened, it only happened according to the rules in the logic. And then This gives us a full picture where the logic from one side makes sure that it remains persistent, and on the other side it ensures that the state is only changing according to the logic. And it's all being done by the spender providing the transaction data. Did you follow me so far? Yes? More or less? Okay. Here's an example. So this example is actually exists at least in 2 places. And if you want, come to me after, I'll give you a repository and you can play with this particular example. It's a covenant that enforces, or smart contract that enforces a counter, on-chain counter. So how does it work? The logic obviously has to still enforce the same thing, which is the first output in the transaction is always the same, has the same address as my own. By the way, you cannot write it in the program directly because the address is created after the program is created, but you can provide the program with a reference to its address and then it can check it. Yeah, I think. And then the next thing that the program will do is it will check that whatever is written here, in this case is 1, and whatever is written in the new output, the difference between those 2 numbers is 1. And this gives you basically an option to maintain. It's a very useless smart contract, but you see the point, like just to demonstrate how the only thing you can do, everyone can spend this counter, but the only thing they can do is progress this counter by 1. They cannot, if there is money here, they can never take it. They cannot decide that there will be 3 outputs, anything like that, because there is a very strict enforcement. Or they cannot decide to write 1 and then 3. It has to progress in the same order. One comment I will make here is that you can see from this example that there is still concurrency issue, right? Because if I want to call this and somebody else want to call this, we both are going to provide some transaction data that rely on some state. But then if one of us will succeed before the other, then the second one that will provide the data will be referring something that doesn't exist anymore, right? So it is still, there are still some concurrencies issues to consider. Okay. Not many more slides. I think 2. So here is something that I think would be much better. Or maybe, what is one main issue with this suggestion? It works, right? But the problem here is that you need to write the contract logic in script. And I think it's, because of all the moving parts, it's not going to be as accessible to many, many developers around the world. I mean, there are many, many nuances, and if you want to write something complex, there is a good chance you will make mistakes and you will create bugs. So a different, perhaps more safe one, is to work on this structure once, and then I'll show why it helps. This structure is the following. It's the logic of the witness program of the smart contract is, now I define it to be a Stark verifier. What does it mean? It means that the logic now says, here is a way to verify a computation, and I also specify particularly which computation I intend to have here. There is like some representation of some program in a language that I will call Cairo from now on, but it can be any other language, it can be Rust. And the only thing that, in addition, is that there will be the covenant logic. So the only 2 things we have in the witness program, in this logic of the smart contract, is a Stark verifier for a particular program, the smart contract program that we care about, and the covenant logic that we mentioned earlier, okay? And then, what is the advantage of something like this? Sorry, I didn't explain everything, sorry. And instead of state, I propose that you don't have to push the state explicitly, but instead, you just use commitment of the state, meaning you take the state, you represent it in some standard way that needs to be defined, and then you Merkleize it, and you only put here the Merkle root of this state. And what the proof, and then in order to spend this transaction, you need to provide to the verifier with a proof that says, I run this program, and now maybe program is misleading here. I mean the Cairo program. I run this Cairo program on the state that is being represented by this state root, and I received an output of the state that is a new state that is represented by this state root. And you will submit this proof. The verifier in the logic here will verify the proof. The verifier in the smart contract will verify the proof, and only if it's valid proof and all the other conditions of the covenant are being fulfilled, meaning it's replicated to a verifier and the state root is whatever the proof is saying, then it will let you spend. Why did I push all this complexity in? Because the previous one was simple, right? And this one is complex, so why? It has, so here's the value. We do it once, it's very complex, but we spend a lot of time auditing it, documenting it, making sure that everyone can understand it. And then you have a template that you can work with, that you can write logic in a reasonable language, such as Cairo, and you don't have to deal with script because someone created this template for you. And then you can create a smart contract with any language in the world, Cairo in particular, progress it by sending transactions that are proof of the execution of this contract. And this also potentially, depends on how it's structured, it can save cost. If this contract is doing many things at the same time, then it can save cost and also can reduce all kind of things that relate to covenants that I won't touch. Now, you don't have to go with this more complex proposal. You can also do this. This is a template that we already have, and you can go and play with it and install like simple smart contracts. And in many ways, this is better. It's cheaper. If you have like simple logic and small things to do, it's probably better. But if you want like complex logic and you're like and complex programs, and you still want to once in a while run them, then perhaps this could be better. And this is something we are working on, meaning we're working towards a full-fledged verifier in script. I hope we will have a version soon. It's all based on opcat, meaning it doesn't work today. It requires like the proposal of opcat to be implemented, but it also won't be cheap, meaning calling this transaction will probably be, I don't know what, $1,000. So it's not something you will do for like everyday life. For the everyday life, you probably want to use the simple one. But if, for example, you want to construct an L2, then probably this is a better structure. If you want something that you only call once in a very long time, but it has a complex logic software or that deals with many users behind the scene, then maybe you want to use that one. That's it. I think I covered everything I wanted. Yeah. So I hope it was clear. Thank you.